Minasan konnichiwa, Zamurai Engineer this. In this video, let us continue with the numerical solution using Gaussian elimination of simultaneous linear equations. By implementing determinant of a square matrix using a Gaussian elimination. So let us proceed with an example. And starting with the theorem of determinants. It says that if a multiple of one row of a square matrix, so this is a symbol for square matrix because this matrix A is n by n. So it is a square matrix is added or subtracted to another row of a square matrix to result in B matrix, which is also a square, then determinant A is equal to determinant B. Okay. Take a look. Let's understand it by slowly reading and internalizing the meaning. If a multiple row, so this matrix has several rows, 2 or more. So if 2 or more, okay, if a multiple of one row of a square matrix, okay, a multiple of one row is added or subtracted to another row, okay, of another of that same matrix to result in matrix B, okay. So we have a matrix A, which is n by n, and we have matrix B, which is n by n. So let us just focus on matrix A, which is n by n. If one row, there are multiple rows, but if a multiple of one row, okay, so meaning 2 or more rows, okay, multiple of one row, meaning of multiple one row is multiplied by something, some constant number, okay. So for example, if we say multiple of 2, so we have to multiply by 2. Multiple of 3, we have to multiply by 3. So meaning if a multiple of one row, okay, meaning we have different values on the elements of one single row in a row of that matrix is added, okay, multiple, meaning we have to multiply that row by some constant, and after multiplying that is added or subtracted to another row of that same matrix, and it results in B matrix, okay. It resulted in B matrix after adding or subtracted. Then the determinants of matrix A and determinants of matrix B are the same. Okay, so that is the theorem. Okay. So, the determinant of an upper triangular matrix A, which is n by n, is given by, okay, how to calculate determinant. Determinant A is equal to A11 times A22 times A33 times AII times up to the ANN. So that is a product upper triangular matrix, because we are looking at upper triangular matrix already. So other elements aside from these numbers, A11, A22, A33, and so on, AII times something up to ANN. Other than this, will become zero because there are zeros all around the lower triangular matrix. Because we are talking here of upper triangular matrix, the upper triangular elements are not zero, but the lower triangular elements are all zeros. So that's why there is only one product in the determination of determinants, and this is the only product. Okay, so that is a critical second theorem. So we have the first theorem, second theorem. Critical for our understanding of this matrix manipulation. Actually, we are just reviewing this because you already have these things on your previous mathematics subject. Matrix operation. Forward elimination by square matrix. Using forward elimination to transform matrix A, which is n by n, to an upper triangular matrix U, which is n by n. Okay, how to do it? Okay, matrix n by n, matrix A, which is n by n, going to matrix U, which is n by n. Okay, let's transform. Their determinant should be the same. Because of what? The first theorem. Because of the first theorem. So the first theorem, and we are able to use that as use that first theorem as a basis for this. So therefore, example, let us perform it using the example which is already given on example 1. That's our example 1. So this is our, I think this is the third example or fourth example. Using the Gaussian elimination, find the determinant of the following square matrix. So it is more complex if we do it right now rather than do it after converting this into upper triangular matrix. So matrix U is an upper triangular matrix. Okay. So that's why it is called U. U matrix is upper triangular matrix. So let us continue. Forward elimination step. So divide equation 1 by 25 and multiply it by 64. That is an operation which we need in order to eliminate the first term of the second equation. Okay, so we have the first row to be equal to this one and then subtract it to equation 2. This is the equation 2. Subtract by this. So what will happen? So this is the result. Okay. So then replace, it will become like this. Then do it similarly for elimination of the first coefficient of the third row. This one, we have to eliminate this. Do the same process. Okay. And how to do that same process? So we have to divide by 25 and multiply by 144. Divide by 25, multiply 144. So it will become what? 144 on the first term. And because of that, subtracting it to the third row, it will become 0. So we are able to make the third term 0 also. So we have both the first term of second and third row to be 0. So that is nice. And let us move to the next operation, which is we want this one to be 0. That's why we need the second row. Second row, which is our equation 2, divide by negative 4.8 and multiply by negative 16.8. So, and our second row will look like this. Okay, and subtract to the third equation. So subtracting will become 0, 0, and 0.7. So we are only talking here of matrix, not equation actually. We are just talking here of matrix. Unlike on the previous sample, we are what? Operating on the whole equation. We are just operating on the what? The coefficient of the variables. Okay? Take note of that because that is somewhat different because we are just converting the matrix A into upper triangular matrix. Okay. So after that forward elimination, we have the what? The upper triangular matrix. And therefore, if we want to solve the determinant of this, we just have to multiply this 3. 25, which is A11, times negative 4.8, which is A22, and multiply by 0.7, which is A33 or ANN. We cannot find any other values because multiplying this one, and this one will become 0. This one will become 0. This one, all the other values are 0. That's why this is the only value of the determinant, and that is actually equal to negative 84. Okay, multiplying that, this one, 25, negative 4.8.7, negative 84. In 4 significant figures, we have negative 84.00. Okay, so let us summarize our operation. We're able to discuss all about Gaussian elimination, its forward elimination process, the backward substitution process, the notable pitfalls that should be avoided, the improvements that we incorporated, particularly the partial pivoting, and lastly, we have the determination of determinant, finding out the determinant of the matrix, which is just what? Determinant of matrix is equal to the determinant of the upper triangular matrix. Okay, so therefore, there is another function, there is another usefulness in in computing the upper triangular matrix. Okay, and that's all for the first method in trying to numerically solve simultaneous linear equations. Again, this is Dr. DrEYPEI, preaching engineering for nation building.